In this lesson, we will focus on the drilling, reaming, and boring techniques and tool applications in Project 1, specifically on Task 1.3, key points of drill bit sharpening and group drill sharpening techniques. The quality of drill bit sharpening directly affects the quality and efficiency of drilling. As a specially improved type of drill bit, group drills have unique sharpening techniques. Next, we will delve into these core aspects in detail. In metal cutting processes, drilling is a fundamental and important machining operation. The sharpening quality of the drill bit plays a decisive role in the precision, surface quality, and efficiency of the drilling process. Key points of drill bit sharpening. Point angle. The point angle is a critical parameter of a drill bit. It is the angle formed by the projection of the two main cutting edges on a plane parallel to the drill bit's axis. The standard point angle for a twist drill is typically 180 degrees. When machining different materials, the point angle needs to be adjusted accordingly. For instance, when working with hard materials, the point angle can be increased to enhance the strength of the drill bit. Conversely, when machining soft materials, the point angle can be reduced to facilitate smooth chip evacuation. In actual production, if machining soft materials like aluminum alloys, the point angle can be ground to 130 degrees to 140 degrees. For hard materials like alloy steel, the point angle can be ground to 125 degrees to 135 degrees. Relief angle. The relief angle is the angle between the main flank surface and the cutting plane. Its function is to reduce friction between the main flank surface and the machined surface of the workpiece. If the relief angle is too large, the cutting edge strength of the drill bit will decrease, making it prone to wear and chipping. If the relief angle is too small, friction increases, leading to higher cutting temperatures, which can also affect the drill bit's lifespan. For standard twist drills, the relief angle near the outer edge ranges from 8 to 14 degrees and gradually increases from the outer edge towards the drill center. This is because the cutting speed is lower near the drill center, resulting in more severe friction, thus requiring a larger relief angle to reduce friction. Chisel edge angle. The chisel edge angle is the angle formed by the projection of the chisel edge and the main cutting edge on a plane perpendicular to the drill bit's axis. For standard twist drills, the chisel edge angle typically ranges from 50 to 55 degrees. The size of the chisel edge angle is related to the relief angle and the point angle. When the relief angle is ground too large, the chisel edge angle decreases and the chisel edge length increases, which can increase the axial force on the drill bit, making drilling less efficient. Therefore, it is important to reasonably control the relief angle during sharpening to ensure that the chisel edge angle remains within an appropriate range. The symmetry of the two main cutting edge lengths and the point angle. The length of the two main cutting edges should be equal, and the point angle should be symmetrical about the drill bit's axis. If the length of the two main cutting edges are unequal, or the point angle is asymmetrical, it can cause the drill bit to deflect to one side during drilling, resulting in a drift phenomenon. Drift can reduce the positional accuracy and dimensional accuracy of the drilled hole and increase surface roughness. For example, when machining high-precision mechanical parts, if drilling results in drift, it may render the entire part unfit for assembly, leading to scrap. This necessitates careful observation and adjustment during drill bit sharpening to ensure the symmetry of the two main cutting edges. Cluster drill sharpening technology. Characteristics of cluster drills. Cluster drills are modified and improved based on standard twist drills. They have advantages such as good chip breaking and separation, reduced axial force, and excellent cutting performance. The structural characteristics of cluster drills mainly include the sharpening of the chisel edge, the grinding of crescent grooves, and the sharpening of the main cutting edges. Sharpening the chisel edge. Sharpening the chisel edge is one of the significant improvements in cluster drills. By shortening the chisel edge, and increasing the rake angle at the chisel edge, the axial force during drilling can be significantly reduced, enhancing the centering performance of the drill bit. For example, when machining deep holes, reducing the axial force allows the drill bit to maintain linear feed more easily, preventing drift. When sharpening the chisel edge, it is important to control the length of the chisel edge and the size of the rake angle. Generally, the chisel edge length is reduced to 1/5 to 1/3 of the original length, and the rake angle at the chisel edge can be increased to between 0 and 15 degrees. Grinding crescent grooves. Grinding crescent grooves on the main cutting edge divides it into several segments, forming chip breaking grooves. This narrows the chips, facilitating chip removal. Additionally, the crescent grooves increase the effective rake angle of the cutting edge, reducing cutting force and cutting temperature. When grinding crescent grooves, attention should be paid to the depth and width of the grooves. The depth of the grooves is generally between 0.2 to 0.5 mm, and the width is determined by the drill bit diameter, typically ranging from 0.1 to 0.2 times the drill bit diameter. Sharpening the main cutting edge. Sharpening the main cutting edge can improve cutting performance. Generally, the main cutting edge is ground into a zigzag or arc shape, which increases the working length of the cutting edge and distributes the cutting load more evenly. For example, when machining tough materials, sharpening the main cutting edge can make chips break more easily, thereby improving machining efficiency. Integration of ideological and political elements. From the seemingly minor issue of drilling drift, we can see its potentially fatal impact on the machining quality of the entire part. In metal cutting processes, every detail is crucial. Just like during drill bit sharpening, even slight deviations in parameters such as the point angle, clearance angle, and chisel edge angle can lead to a decline in drilling quality. This requires us to cultivate a spirit of craftsmanship that strives for excellence and meticulousness in our studies and work. When sharpening drill bits, we must take each step seriously, repeatedly checking and adjusting to ensure that all parameters of the drill bit meet the requirements. Only in this way can we produce high-quality parts and contribute to the development of the manufacturing industry. Practical application case. In the machining of automobile engine blocks, a large number of holes need to be drilled. If the drill bit sharpening quality is poor and drift occurs, it can result in the positional and dimensional accuracy of the holes not meeting the requirements, thereby affecting the performance and reliability of the engine. Using cluster drills for machining can effectively reduce axial force and improve the accuracy and efficiency of drilling. At the same time, reasonable sharpening parameters can extend the service life of the drill bit and reduce machining costs. For example, an automobile manufacturing company improved its drill bit sharpening technology and used cluster drilling to machine the holes in engine blocks. This reduced the defect rate of drilling from the original 5% to 1%, while also increasing machining efficiency by 30%. In this lesson, we focused on the key points of drill bit sharpening and cluster drill sharpening technology in Task 1.3 of Project 1. We first explored several critical aspects of drill bit sharpening, including the point angle, clearance angle, chisel edge angle, and the symmetry of the two main cutting edges, all of which directly affect the quality and efficiency of drilling. We then studied the sharpening technology for cluster drills, which through improvements such as chisel edge sharpening, grinding crescent grooves, and sharpening the main cutting edge, exhibit better cutting performance. Additionally, by analyzing the drift issue, we recognized the importance of cultivating a spirit of craftsmanship that strives for excellence and meticulousness in the machining process. Finally, through the case study of automobile engine block machining, we observed the practical application and the effectiveness of these technologies in actual production. I hope that in your future studies and practice, you will be able to master these techniques proficiently and improve your machining skills.